I deliberately kept the abstract for this fairly vague because I wasn't sure what would be most of interest to people. And I've got a large number of slides prepared ranging from the basic observational evidence for dark matter going right the way through to the thing that I work on, which is the astrophysical uncertainties behind looking for dark matter. So before I get started, what I'd like to do is ask you guys some questions and try and get a feeling for what your backgrounds are and what you're particularly interested in. So I guess the first question is, stick your hand up if you consider yourself to be an astronomer. Okay. How about if you consider yourself to be a particle physicist? And I suppose the final one, if there's anyone left, astroparticle physicist. Okay, so there's a mixture, but with the bias towards the particle physics side. Okay. And how about if you think you're a theorist? Okay, so that means the majority of you are observers, experimentalists, somewhere in the middles. Right, so I had been wondering about skipping the overview of the observational evidence for dark matter, but given that the majority of you have particle physics backgrounds, would you like me actually to go through that? I'm seeing some nodding, so let's do that. Okay, so the structure I've got there, the question is, why do we want to detect dark matter? What is it we're trying to detect? And how do we do it? So let's start with the why, or in other words, the observational evidence for dark matter. So it wasn't the first piece of observational evidence, but it's probably the cleanest single piece of evidence. It comes from looking at galaxy rotation curves. And I should say at this point, if there's anything I say that you don't understand, then please stick your hand up and wave at me and ask questions if there's anything I'm saying that's not clear. So spiral galaxies are made of a disk of stars, and those stars move in circles due to the force of gravity. And so that's just like the solar system. And in the solar system, the inner planets are going around really, really fast. As you get to the outer ones, they're going around really, really slowly. So naively, you'd expect exactly the same thing to happen in spiral galaxies, but you don't. So what you do is you use the Doppler effect to measure the speeds of stars and clouds of gas in the spiral galaxies as a function of their distance from the center. And this is called a rotation curve. And so what you do is you plot those speeds as a function of distance from the center. And what you'd expect, if all the material in the galaxy was the stuff you could see, the disk of stars, then those speeds should fall off like this, roughly as 1/r². What you actually find is that the stars in the outer regions, they're flying around really, really fast. And the analysis of this is really straightforward. It's just Newton's laws of gravity. Acceleration of something going around in a circle is v²/r, equal to the gravitational force, which is g, the mass inside that radius, divided by r². And so we've got this observation that speeds are roughly constant. Stick that on the left-hand side here, and what it's telling us is that the mass within a given radius isn't constant, it grows as you go further out. So you can also change a mass into a density, and it's telling us that there's this extended distribution of matter, called a dark matter halo, whose density varies as 1/r², very roughly. Now, this is very straightforward. The only things we've assumed are Newton's laws of gravity. So if Newton's laws of gravity are correct, then galaxies are surrounded by halos of invisible matter.
Is there like a straightforward relation between this constant and the radius of the galaxy under consideration?
Sorry, which constant?
Constant speed, constant velocity.
Okay, that's a very good and quite sort of technical question, and it typically depends on the size of the galaxy. The more massive the galaxy, the faster things are going.
Linearly?
No, there's actually something called the Tully-Fisher relation, and I must admit I can't remember it off the top of my head. But so roughly there is a relationship, but it's not as simple as you might naively think. Right, so any more questions on galaxy rotation curves before we move on? Right, so we'll move out in scale. Galaxies don't live on their own, randomly scattered through space. A lot of them live in what are called galaxy clusters, gravitationally bound groups of tens, hundreds, or even thousands of galaxies. And in fact, the first suggestion that dark matter exists goes right the way back to a guy called Zwicky in the 1930s. So what he did was use the Doppler effect to measure the speeds of galaxies within a cluster called Coma. And in very simple terms, what he found was that the galaxies were flying around really, really fast. So fast they should just fly off into space rather than being bound together in a cluster. And so he was the first to suggest that dark matter should exist. The physics behind this is actually something called the virial theorem. If you've got a self-gravitating system, so held together by gravity, which is in equilibrium, then its kinetic energy K and its potential energy V are related with a simple relationship here. And so the idea here is to relate the kinetic energy and the potential energy to quantities you can measure and the total mass. So the way this works, kinetic energy is just the sum of the individual kinetic energies of the galaxies. Potential energy, you sum up over all the galaxies. And then the average speed is just the sum of the mass-weighted speeds divided by the total mass. So it turns out the way to do this is to define something called the gravitational radius that happens to be defined like this. And then once you've done that, you can then find an expression for the total mass of the galaxy cluster in terms of that gravitational radius and the average mean speed squared of the galaxies. So the Doppler effect allows you to measure the average mean speed squared, and you can estimate this gravitational radius by looking at the projected positions of the galaxies on the sky. And obviously I'm skipping a lot of technical details here, but once you do this, you come up with an expression for the total mass of the galaxy cluster divided by its total luminosity, L, in terms of the ratio of the mass and luminosity of the sun. So when you see any of these dots with circles around, that means the sun. So the galaxy cluster has 400 times as much mass per unit luminosity as the sun. And you might imagine that galaxies were made of stars that were typically fairly similar to the sun, so you wouldn't necessarily expect this factor in here to be 1, but you certainly wouldn't expect it to be 400. And it's another way of telling you that there's an awful lot more mass there than the light we would expect from the light you can see. Another thing we can do with galaxy clusters is look at them using X-ray telescopes. So in fact, galaxy clusters don't just contain galaxies, they contain large amounts of hot X-ray emitting gas. And so here on the right, we've got a sort of familiar optical image of the Coma cluster where you can see the galaxies. But when you look at it, and this is on roughly the same scale with an X-ray telescope, you see all this X-ray emission that's coming from the hot gas. And so again, this allows us to work out something about what the galaxy cluster is made of. And so the way the physics of this works is you assume the gas is in equilibrium and spherically symmetric. And in that case, the pressure force, which is 1 over the density times the pressure gradient, is equal to the gravitational force. The two balance. If you then use the ideal gas law for the equation of a state of a gas, pop that into the left-hand side, and you end up with another relationship for the mass within a given radius. And so again, what we've done here is try to write the left-hand side in terms of things we can measure. The temperature gradient with radius and the density gradient with radius. And it turns out that you can measure those things, the temperature gradient from the X-ray spectrum, that is the energy of the X-rays, number of X-rays as a function of their energy, and the density gradient you can measure from how the surface brightness of the X-rays varies. And when you do these things, what you get out is a value of what's called the baryon fraction, the fraction of the total mass of the galaxy cluster that's in the form of baryons. And the result that you get when you do this is about 0.13. So in other words, the vast majority, about 85% of the mass within a galaxy cluster is non-baryonic. So
this is based on the assumption that this Coma ratio that's due to the mass, and not that for some reason it's less luminescent than you expect. That there's like dust in between.
So that objection would have been absolutely valid here, possibly, but it's not so much how X-ray bright it is, it's how things vary with radius. So if you'd want to explain this with dust, you'd have to have dust doing odd things, I think. Yes. But nonetheless, I think your underlying point might be valid in that astronomical observations are difficult. They have systematic errors. And in particular, the things which go in here, we've assumed equilibrium. That's probably not necessarily true, as we'll probably see later. Galaxy clusters don't just exist in isolation. Many of them are having ongoing formation. They're not necessarily spherical. And there's also various uncertainties that go into the modelling here, for instance, going from the temperature of a galaxy cluster to its mass. So this is indicative, but you certainly shouldn't take this too seriously. And the first thing which should be ringing alarm bells here is the lack of an error. So I think I'm telling you about this because it's part of the story, but we'll see later on there are actually nowadays more accurate ways of measuring the baryon fraction. Turns out they give an answer that's roughly consistent with this, and that's good. It's good to have cross-checks on things. But this is a sort of messy astronomical technique. So any more questions at this point? So please, other people, ask questions too. So one more thing to say about galaxy clusters. And so we've so far seen that we've got evidence for dark matter, and we've got evidence that dark matter is non-baryonic. The development over the last 10 or 15 years is that we've been able to map out the mass distribution within galaxy clusters. And this is a much, much cleaner measurement. So this is coming simply from the fact that Einstein's gravity tells us that matter bends space, and once space has got bent, the light gets bent going through it. And in particular, one of the best ways of doing this is to use what's called strong lensing. So here we've got an example of this. So in the middle here, we've got a very big galaxy cluster. And what's happening is we're looking at a small galaxy that's sat behind it at a huge distance. It just happens fortuitously to be sat straight behind it, so the light gets bent as it goes round. And so instead of seeing a single image of the galaxy cluster, we see these multiple images. And if you actually zoom in on this picture, you can see that these are actually completely identical. It isn't multiple weird shaped things, it's multiple images of the same single galaxy, the light's getting bent. And so by looking at the brightness of these images and their positions, you can map out the mass distribution in the galaxy cluster. And that's what we've got here on the right. The spikes correspond to the galaxies you can see. And then this mound in the middle, that's the dark matter that we can't see. So a slightly more famous example of gravitational lensing in dark matter is something called the bullet cluster. So how many of you have already heard of that? Stick your hands up. Okay, so most of you, but still I think it's probably worth going through in a little bit of detail. So I guess it's nearly a decade ago now that this actually led to some excitement, and then a paper entitled Direct Empirical Evidence for the Existence of Dark Matter, which is a pretty bold claim. So this is what they did. So what we've got here is a galaxy cluster. And what we've got over here is a smaller subcluster. It's one of those things that to the untrained eye you might not spot, but there is an overdensity of galaxies here. That's what you see when you look at it with the Hubble Space Telescope. However, when you look at it with an X-ray telescope, you see something very different. You see this thing on the right. And so we've got a big lump of hot X-ray emitting gas, and then a smaller one, which is bullet-shaped like this. And so what's happened is that these two things are in the process of merging. The little galaxy cluster has gone through the big one and out the other side. Or at least that's what the galaxies in dark matter have done, because they don't interact. On the other hand, the X-ray gas does interact, and it gets caught up in the middle, and in particular you get this shock front as the gas from the small subcluster tries to push its way through. And so we already know that most of the baryonic matter in a galaxy cluster is in the form of the X-rays. And so this map here is not just telling us where the X-rays are, but it's telling us where we expect most of the baryonic matter to be. However, what you can also do is use gravitational lensing, weak lensing it turns out in this case, which is not where you get multiple images, but where you just get distortions in the shapes of galaxies. But you can use that in the same sort of way to map out the mass distribution. And that's what this plot on the bottom left is. These contours show the mass distribution from the lensing analysis. And the total mass distribution follows the distribution of the galaxies rather than the distribution of the dominant baryonic matter. So this is undoubtedly pretty strong evidence for non-baryonic dark matter. The one caveat going into this, though, is to do this lensing analysis, you have to assume general relativity. And we kind of already knew that if you assume general relativity is correct, then we have good evidence for dark matter existing. Now, there are theories of modified gravity. I won't say very much about them. There's one called MOND, Modified Newtonian Dynamics, which was designed to explain these observations of galaxy rotation curves. And it does what it was designed to do very, very well. However, MOND's phenomenological, it was something which was just designed to do that job. People have worked on it, developed it. There's now something called TeVe's tensor vector scalar gravity, which is a cosmological generalization. Now, the question would be, could those sorts of theories explain these observations without dark matter? And the question isn't really answered because these modified gravity theories are so absolutely hideous that it's really, really difficult to do these calculations. People have sort of done a half calculations, but nobody has definitively shown that modified gravity theories can't do this. It would seem unlikely that you could have a mass distribution that looked like that produced lensing contours that look like that. It would have to be something really, really weird. But nobody has actually disproved at this point that modified gravity theories can't do this. So the point of this whole deviation is that this is another piece of good evidence for dark matter, but it's not quite the definitive thing that the title of the paper and some of the sort of publicity that went around it might have claimed. So, any questions on galaxy clusters? Right, so what we come to now is the cosmic microwave background radiation. And this is probably the most single powerful tool in cosmology. Not just for dark matter, but for so much of what we know about the universe comes from the cosmic microwave background. So the cosmic microwave background radiation is a background of thermal relic photons. They're left over from the Big Bang. So at very early times, the universe is very hot and dense, and the atoms are all ionized. About 400,000 years after the Big Bang, atoms form and the universe becomes neutral. And so at that point, instead of scattering off of things all the time, the photons start streaming through space. And they stream towards us today. And as the universe expands, they get stretched, so their temperature drops. And the existence of this radiation is one of the most powerful pieces of evidence that the Big Bang is the correct description of our universe. However, it's not the radiation itself, but it's the anisotropies in the radiation that are really interesting. So the temperature is roughly 2.7 Kelvin, but there are tiny fluctuations in different directions that are about 1 part in 10 to the 5. And so these fluctuations come from small initial fluctuations in the distribution of matter and energy in the universe. What we think is that there are initial small fluctuations possibly generated by something called inflation that happened just after the Big Bang. We don't know that for sure, but we do know to some degree of confidence that there are these small initial fluctuations that then grow due to the force of gravity. Gravity pulls things in, the fluctuations get bigger, and they collapse to form galaxies and galaxy clusters. That all happens in the late universe, though. In the early universe, these fluctuations essentially provide potential whales, and the cosmic microwave background photons have to climb out of them. And that leads to fluctuations in their temperature. And those temperature fluctuations, well, they depend on various things. Firstly, they obviously depend on the very initial fluctuations, but they also then depend on how those initial fluctuations grow with time up until the point that the microwave background radiation was released. And the growth of the fluctuations depends on what the universe is made of. And so by looking at the scale dependence of these fluctuations, we can learn what the universe is made of. So the fluctuations were first detected in 1992. Most recently, they've been studied to really high accuracy by a satellite called WMAP that's just come to the end of its useful life. And these are its final results from its 9-year data set. So these are the temperature fluctuations with the mean temperature subtracted off. The red regions are hot spots, blue regions are cold spots. And the first thing you sort of notice when you look at this, there are some blobs of different sizes there, but typically there's a characteristic blobbiness scale, which is about a degree across. And it turns out that the characteristic scale of these fluctuations is the length scale, the size of the universe at the time the radiation was emitted. That's a length scale. What we see when we look at the sky is an angle. And that angle depends on the geometry of the universe. In flat space, it has a particular size, and if space is openly curved, the angles are bigger, and if it's negatively curved, they're smaller. And so by looking at how big the angles are, it allows us to measure the geometry of the universe. Well, why is that interesting? Well, the geometry of the universe depends on the energy density. There's a critical energy density for which the geometry is flat, and then if the energy density is bigger, the geometry is closed, and if it's smaller, the geometry is open. So it turns out that this characteristic scale, which shows up in this plot here as this peak, is pretty much exactly where you'd expect it to be if the universe is flat. So that's telling us that the total energy density in the universe is very close to the critical energy density for which the geometry is flat. So, as cosmologists like to do, we like to write things in terms of density parameters. Omega, where omega is the density of whatever species you're interested in, matter, baryons, radiation, divided by this critical density for which the geometry is flat. So the latest CMB data sets measure omega to be very close to 1, to within really high accuracy. You don't need to worry too much about those exact numbers there. What you need to worry about is that this is very close to 0 and the error bars are very, very small. Now if we come back to this plot here, this is the angular power spectrum. It's telling us about the typical temperature differences between directions that are separated by a particular angle. And so we've got the angular scales on the top here. So 90 degrees here going over to smaller and smaller scales here. So this first peak tells us about the geometry and hence the total energy density. But there's an awful lot more information in these subsequent peaks. And the physics they're coming from is we've got a competition. Gravity's trying to pull things in, but pressure in the baryons is trying to stop them collapsing. So you get these oscillations set up. And that's what we're seeing here. They're called Doppler peaks. And the amplitude of these oscillations depends on the relative amount of dark matter and baryons. And so by looking at these peak heights, we've also been able to measure the baryon density parameter and the cold dark matter density parameter. In both cases, it turns out it's not actually just the density parameter you measure, it's the density parameter times little h, where little h is related to the Hubble constant, the rate at which the universe is expanding today. So the Hubble constant is about 72 kilometers per second per megaparsec. And little h comes from writing it like this. So I've just said it's about 72, so little h is about 0.72. So this thing here is roughly little h 0.72. Again, don't take too much notice about the exact values of these numbers. The point is that the error bars are very, very small. So I told you before that you could sort of measure the fraction of baryonic matter by looking at galaxy clusters. You can now do this much, much, much more accurately using the cosmic microwave background radiation. So, any questions about the cosmic microwave background radiation?
So is therefore Planck satellite right now, right?
So that's an extremely good question. Planck's been up there for a few years now, busily taking data, about to come...
Like the same thing, or what's their plan?
Right, okay, so what Planck is doing is basically the same sort of thing as WMAP, scanning the whole sky, but lots finer resolution. So that, must admit, I can't remember numbers off the top of my head, but so it's going to be able to measure more of these wiggles. However, and maybe at this point I should actually get out some slides from another talk because that would answer your question rather better. There are actually already other experiments that are doing that, things called ACT and the South Pole Telescope. And so my talk I'm going to give tomorrow, I had that on a slide, so let's...
You can't give Planck spoiler graphs.
One of my colleagues in Nottingham does indeed work on Planck, and not a word is coming out of his mouth, so don't worry, I know nothing. So the plot I was actually going to show you is, of course, not Planck data. It's the WMAP data we've already seen, these first 3 peaks, and then these additional data from the South Pole Telescope and something called ACT. So you can see that they've actually already measured all this sequence of higher things. So Planck is firstly going to do the same but with smaller error bars. It's also eventually going to measure what's called polarization. I probably won't go into that because we could spend too long going off on a deviation. But it's going to beat these error bars down substantially. However, I think, to be fair, the excitement about Planck isn't going to be coming from better measurements of the dark matter density. It's going to be coming from other things that it might be able to do. For instance, measuring the shape of the initial fluctuation spectrum. That's the $60 million question. So again, this is a bit of a deviation. Tensor modes are gravity waves that could have been generated by inflation just after the Big Bang. We don't know what their amplitude is. It really depends on the underlying physics. There are some small class of models that have already been ruled out, but by the fact we've not seen them. There's a class of models that Planck could see, and then there's a whole bunch more models that Planck definitely won't see. So if Planck sees the tensor modes, we'll get very excited because this is the closest thing to a smoking gun for inflation. Your guess is as good as mine. So actually, so coming back then to the CMB, anybody got any more questions? Or anything? But go on.
This microwave background radiation, the time constant, I mean, is it changing with time? If you measure it 10 years later, will it be different?
So one thing which will certainly be different is the temperature. That will go down uniformly as the universe expands and things. Well, it'll be different, but in 10 years' time, the difference will be negligible. You'd have to come back in like 2 billion years' time. So on our sorts of timescales, it's completely stable. Changes over cosmological timescales, person timescales, it is effectively constant. Anything else? And I really don't mind how simple it is, so yeah, fire away.
What's on the y-axis of this?
As in there.
Yeah.
So this is this quantity called the angular power spectrum, and it's sort of related to the thing I said in words, which is basically the mean temperature difference between scales that sort of... It comes, you take it, you expand it in spherical harmonics, you average over the spherical, but I sort of deliberately fudged that since it gets a bit technical. But mean temperature difference is a practical. Yeah.
This WMAP, it seems like randomly, but there are some correlations in it, right? On this.
Indeed, the phase is certainly not random.
So can they numerically generate that WMAP image?
So there is an element of randomness in it, as in if you took that power spectrum, you could generate different realizations that would have the same statistical properties of this, but they wouldn't necessarily be the same in detail. So there is an element of randomness as to which directions in particular are hot spots and which are cold spots. Does that answer your question? Up until now, what we covered in the first part is why dark matter, the observational evidence, and very briefly what, weakly interacting massive particles. What we're going to come on to now is how to detect WIMPs. But before we do that, anyone got any more burning questions about the why and the what? So even if not, one thing, because I think several people asked about this, and I've got a picture from another talk which might answer, is coming back to galaxy clusters and gravitational lensing allowing us to map out the mass distribution. And it's this additional picture up the top that probably makes clearer what's going on. So here we are sat on Earth. We've got this big galaxy cluster, and we're looking at a distant little galaxy sat behind the galaxy cluster. The galaxy cluster bends space, so the light from the galaxy doesn't travel in a straight line, it gets bent around the galaxy cluster. However, when we look at images, our brains analyse them as if the light was travelling in straight lines. So instead of thinking, well, we've got a single galaxy, but it's travelled the light along multiple bent paths, what it actually looks to us is instead of having a single galaxy, we see multiple images of the same galaxy because the light from it has come to us along these bent paths. So hopefully that makes what's happening with strong lensing a little bit clearer. So is there anything else from the first part that anybody would like me to say a little more about? Well, we might have some time at the end, but for now then let's press on with the how. So I'm going to focus very much on weakly interacting massive particles. For most of what I'm going to say, though, it doesn't matter what the physics behind them is. It could be supersymmetry, it could be something else. And I'm going to start with the thing which actually probably many of you know more about than I do, and that's using colliders. And so really what you're doing here isn't so much detecting dark matter as making it yourself. The WIMPs are very heavy, you need lots of energy to make them, but the LHC is banging things together at very high speeds. So the public talk version of what you go looking for is missing energy and momentum. The WIMPs would stream out of the detector, leaving no trace and carrying off energy and momentum. Of course, in reality, it's a lot more complicated than that. And my understanding of what you guys are doing is you're looking for events somewhat like this. The two protons come together, produce, say, a gluino and a squark. They decay. Down the bottom end of the decay chains here and here, for instance, you have the lightest neutralino. Along the way, you produce some quark jets. So what you're looking for is the combination of the missing energy and momentum and the quark jets along the way. So that's the limit of what I know about that. So what I would say is if the LHC does produce and detect WIMP-like particles, that would be fantastic. It would be really, really exciting. It would tell us that these particles do actually exist for real in reality. But on its own, it wouldn't solve the dark matter problem. In particular, the WIMPs could nip out of the detector and decay by the time they got to downtown CERN. So to be sure that whatever you detect is the dark matter, you need to know it's stable on cosmological timescales. And then you want, even if things are potentially stable on cosmological timescales, you then need to prove that yes, these things actually are the dark matter in the universe and that they make up galaxy halos. Looking ahead to the future, well, I hope the LHC does detect WIMPs. And then if it does, the next step will be to measure the WIMP properties. And we'll see why this is important later on. The sort of things we'd be interested in are the mass and interaction cross-sections. And the reasons why, well, one of the things that really convinced us that dark energy existed was the plot I showed you here, where you had lots of different observations measuring quantities in different ways and producing consistent results. It may well be that to convince ourselves we've seen dark matter, we have to do it by various different ways, measure the properties and check they're consistent. And then the other thing that we need to do is if you measure the interaction cross-sections, that allows you to go back to your theoretical calculations of the production of dark matter in the early universe and calculate how much should be produced. and check that matches the amount of matter that cosmologists think there is in the universe. So those are the sort of to-do list for collider physics and WIMPs in the future. Any questions about that? Not that I'll be able to answer them if they're very technical. No. Okay, well, we'll move on to the things I do know about. And so the first of these is what's called indirect detection. And the reason it's called indirect detection is that you're not looking for the WIMPs themselves, you're looking for the products of their annihilation. For instance, gamma rays, positrons, and antiprotons. Now, I told you just now that actually, as the universe expands and the density drops, the WIMPs stop annihilating. That's true. However, once structure forms, once galaxies and galaxy clusters form, then whilst the average density is very low, the density within galaxies is very high. So the WIMPs can start annihilating again. And so this cartoon shows what happens here. We're assuming our WIMPs are neutralinos. They come together, produce quarks, leptons, and bosons. These things then fragment and decay, producing all sorts of things. But of course, the things that are most interesting are the unusual things, the high-energy gamma rays, positrons, antiprotons, and possibly neutrinos.
Now we're still talking about the minimal supersymmetric model.
No. So yes and no is the answer. So most calculations are done in that framework.
What's, for example, the status of that neutralino right now with the LHC running?
So again, I'm getting, it's. Can I show you some plots later on, maybe? The parameter space is getting cut into and squeezed of the simplest supersymmetric model, but the problem is supersymmetry is a very broad thing that's difficult to, but I'll probably come back to that. However, almost all of what I'm going to say now isn't so dependent on SUSY. It's more down to the fact that you've got something that's weakly interacting and its own antiparticle, and those are the key parts of the puzzle. Right, so let's have a look about how you go about calculating what you'd expect in an indirect detection experiment. The first thing you need to know is what happens when two particles come together and annihilate. And that's obviously particle physics. If you're then going to go calculating fluxes, you need to know how the WIMPs are distributed through space. And that's largely astrophysics, but with a little bit of particle physics for the initial conditions. And then if you're interested in charged particles like positrons and antiprotons, they propagate through the Milky Way's magnetic field. That's a messy process, and you need to fold that in too. And all three of those things then come together to give you your predicted signals. So let's focus on gamma rays. They travel in straight lines, so they're a bit easier. Phi is the flux, and so we've got d phi dE on the left-hand side. The stuff in blue is all the particle physics related stuff. The stuff in red is the astrophysics. So WIMP annihilation is a two-body process, so it's going to be proportional to the number density squared. And number density is mass density rho divided by mass. So if we look at the astrophysical term, it's going to be an integral over rho squared along your line of sight and over the solid angle of your detector. And then from the particle physics term here, so what I've labelled the different annihilation channels I, so that's just the things that could initially be produced in the decay, and we'll see some examples of that later on. So it's the fraction, Bi is the fraction of the annihilation which goes in via each channel. dN dE is the number of gamma rays that are produced per unit energy for that particular annihilation channel. And then here we've got the mass squared, which is coming from the number density squared. And then unsurprisingly, here's our annihilation cross-section times speed again. So it's how often they annihilate. It's going to be cross-section times speed times number density squared. So those are the bits, and they separate nicely into the particle physics term and the astrophysics term. So let's have a look at the particle physics. So this is then where you do have to have a specific model in mind, and supersymmetry is usually what people have in mind. Now, because the WIMPs are dark, they don't couple directly to the photon. So that means that the vast majority of the gamma rays that get produced are coming from messy processes. Something else gets produced first, for instance, taus or B quarks. They fragment and decay, and largely decay ends up going through the decay of the pi zero. And the net result of all of that is that you end up with the spectrum of the gamma rays as a function. X here is energy divided by mass, is featureless, and obviously cuts off at the WIMP mass. You can't produce something with higher energy than the energy you start with. And the different colours here are for the different possible annihilation channels, and they're all actually fairly similar. It is possible that you can get gamma rays produced directly. For instance, WIMPs annihilating directly to a Z in the gamma or two gammas. And in those cases, instead of having this spectrum, you'd have a line at the WIMP mass. But the WIMPs can't do it directly. They have to do it via a loop diagram, and hence that means that the rate is suppressed. It's typically expected to be very small. Now, the astrophysics input. So the fluxes are going to depend on the density squared. So that very much means you want to go looking where you expect the density to be very large. This is the result of a numerical simulation of the formation of a Milky Way-like galaxy. The bright areas are where the density is very high. So unsurprisingly, density is very high in the galactic centre. But we see also that the dark matter distribution isn't smooth. It contains lots of little small clumps called subhalos. Some of these host dwarf galaxies, some of them are, as far as we know, dark. So those lumps would be a good place to go looking. The ones which are dark, we of course don't know where to look, but the ones which host dwarf galaxies, we can of course go systematically looking there. Now, some sort of technical stuff. There's something which gets mentioned in the literature a lot called the boost factor. And it's basically how much bigger the actual rate is due to this clumping of the density than what you'd expect if the halo dark matter distribution was completely smooth. And some other things to note is that actually this boost factor isn't a single number. Different species probe different scales and regions. The gamma rays, as I've just sort of mentioned, travel in straight lines. So there you're just looking at the density squared along whichever line of sight you're looking at. But the antiprotons and positrons can actually only get to us from a relatively local region of the Milky Way. So then you're probing the density distribution fairly close to the sun. So the boost factor is not a single number. It depends on which species you're looking at. And people have tried to model it and calculate it, but there are huge uncertainties. And I can say a bit more about that later on if you like. The other absolutely huge astrophysics thing, and we'll see some concrete examples of this in a moment, is that there are all sorts of astrophysical processes that can produce antimatter and high energy gamma rays. So it's really important that if you do see something, you've got to convince yourself it's due to WIMP annihilation and not some known astrophysical process. So let's have a look at the current status. Let's start with the gamma rays. And most of the action from gamma rays is coming from the Fermi Space Telescope and ground-based Cherenkov telescopes like HESS, MAGIC and VERITAS. And so these are sort of very much astrophysics things. They're doing huge amounts of astrophysics stuff that's really exciting, discovering all sorts of new objects in the galactic plane that we never knew existed. And dark matter is very much a sideline for these guys. There have been various claimed hints, but there's nothing that's really convincing me yet. There's possibly one exception, which I'll mention in a moment. So before getting on to that, let's actually look at what constraints we get from the fact that we aren't seeing anything. And so as I mentioned before, dwarf galaxies are a good place to look. They're sat within the Milky Way halo, so they're relatively close, and they're surrounded by lumps of dark matter. They're also good because they're little sort of small pathetic galaxies. They don't tend to contain large amounts of stuff like supernovae that would produce gamma rays as a background. So what Fermi has done has looked at about 10 of these things because it's not clear which one is best. So your best bet is to look at lots of them. And then stacked the observations. No sign of anything, so you can place a constraint on the cross section. So here we've got constraints on the WIMP cross section as a function of the WIMP mass in GeV, going from 10 to 100 to 1,000 gigaelectron volts. The dotted line going across here is the cross-section which we think the WIMP should have based on the measured cold dark matter density. Remember, there's this one-to-one link between the cross-section and the density. And then there's a little bit of dependence in the limits on how the WIMPs annihilate. So we've here got mu's, w's, b's, and tau's. But what you're seeing is that things get better as the WIMP gets lighter. That's not at all surprising. That's coming from this 1 over mass squared thing here. And what you're seeing is that for very light WIMPs, at least down at a few tens of GeV, the observations are beginning to get to the point they're excluding the cross-sections which correspond to the measured density. So whilst we're not seeing anything yet, that is already telling us interesting things. I also mentioned the galactic centre is a good place to look because that's the place in the Milky Way where we expect the dark matter density to be highest. However, unfortunately, there's something astrophysical there that is kicking out huge numbers of high-energy gamma rays. And so this has been, back about a decade ago, very accurately measured by Hess. We've got gamma ray flux times E squared as a function of energy, black and red data points, and they're going right the way out here to 10 TeV. And basically, it's very difficult for particle physics models to make dark matter WIMP candidates that heavy. People try to do it. These lines are their best bets. And just basically, you can't come up with a dark matter candidate that's heavy enough to produce the high energy gamma rays of the galactic centre that Hess is seeing. So that's not due to dark matter annihilation and is in fact a background to searches at the galactic centre. But it's not the end of the world. It's more or less a point source. So the trick is, don't look directly at the galactic centre, look slightly away, about a degree away. You get away from whatever the astrophysical source is, and the dark matter density is still going to be pretty high. So that's something that Hess in particular have done. Here again, we've got constraints on the dark matter annihilation cross-section as a function of mass, 100 GeV, 1 TeV, 10 TeV. Here are their limits from looking at dwarf galaxies, so you can see that Hess is sensitive to heavier WIMPs than Fermi. And here's what they see, their limits from looking close to the galactic centre. Here's a bunch of SUSY models. They're sort of getting towards the point they can rule them out, but not yet there. They're going to have to push their sensitivity up a fair bit to do that. Yeah.
So, is there any idea what this galactic, what this astrophysical source could be?
So I think, I'm not 100% sure, but I think the astronomers do have some pretty good ideas. I think we're talking supernovae remnants and things like that. In fact, so one of the things that Hess and also more recently Fermi have done is just mapped out the galactic plane and high energy gamma rays, and it actually is quite common for astrophysical objects to kick out huge amounts of gamma rays.
You mean the bubbles?
No, so not the Fermi bubbles, but really the point source that's sat right at the galactic centre. That's what this spectrum is. Anything else on gamma rays in general? Yeah.
Do you know if there are any future experiments with higher sensitivity to exclude a larger range?
So the big thing that's coming, and I mentioned it in a moment, well, hopefully coming, is a thing called the Cherenkov telescope array, which is an array of these ground-based things. So that's the next thing on the horizon. I think they're beginning to hopefully start thinking of building in a couple of years, full operation in roughly a decade, funding permitting.
Okay. Do you have an estimate of how sensitive they are? If you go back to the
So it's going to push things down by a factor of a few, but I think it's very much a factor of a few rather than an order of magnitude.
okay.
It's going to be much better at lower masses than the ground-based Air Cherenkov telescopes, though. That's what is going to be a big advance. So it is good, it is coming, but it's not a huge step change in what's possible.
step by step?
Yeah. Anything else?
Those ground-based telescopes called Cherenkov because they use this Cherenkov radiation?
Exactly. So what happens, a high-energy gamma ray, as it comes through the Earth's atmosphere, it produces a shower of Cherenkov radiation, and that's then picked off with the mirrors there. So the possible excitement this year in the field of the gamma rays is the possible discovery of a gamma ray line. So as I already mentioned, this would be sort of something that might happen. It'd be really neat, but we expect that the flux will be very low. So a bunch of guys, in particular Christoph Venneger, who I believe is now here in the Netherlands, looked through the Fermi data looking for gamma ray lines, and indeed found one at an energy of about 135 GeV. The initial number was 130, but Fermi have tweaked their calibration and it's gone up to 135. Question of this, how significant it is, and here is the data. And you can sort of see a line in red sat on top of what would otherwise be a sort of declining spectrum. Significance on its own, that's a 5 sigma fluctuation, but this is very much like looking for the Higgs. You don't know where you're looking, so you've got to take into account you'd have also got excited by a peak somewhere else. So once you do that, the significance comes down to about 3 sigma. So people have done all sorts of things. Well, actually, one thing I should mention is the thing that Christoph did that was really cunning was he sort of decided in advance which bits of the sky would be good to look at. So looked at a bunch of theoretical models, well-motivated theoretical models for the density distribution, and then worked out where you were best off looking if you wanted to distinguish WIMP annihilation from the backgrounds. So that's what he did. Other people have possibly found a second line at another energy. Some other people looked at data from galaxy clusters, possibly saw a line at the same energy. Obvious question, what do Fermi themselves say? The published analysis, no evidence for lines, but that was using an earlier data set and looking at different regions. The latest news that I'm aware of, coming from the Fermi Symposium late last year, is that they say they're seeing no globally significant lines, but they do see this feature at 135 gigaelectron volts. And it seems to be coming from various places along the galactic plane rather than a coherent region. But I think what you can say from that is that they're working on this. And we've just got to wait and see. 2 things that are stopping me get excited about this. The first thing is what's called a limb excess. So the limb are gamma rays which come when cosmic rays hit the edge of the Earth's atmosphere. So nothing to do with dark matter, completely well understood astrophysics. However, if you look at that spectrum, there's a line in it. So that sort of rings some alarm bells as maybe there's some systematic that's causing this. The other thing is, if you were expecting a line, you'd also be expecting all these continuum photons, because the gamma rays which come from direct annihilation, that's very rare, so there should be a lot more continuum photons. People have looked, there's no sign of them. Maybe that just tells us that there's an underlying model where it is much easier to produce the gamma ray line than the continuum photons, and there are dozens of theorists cooking up those models, but nonetheless, that is something that's a little bit of a concern. So this is really exciting. It's very nice analysis. It's not sort of theorists dabbling in data and sort of claiming nonsense. They've done this very carefully, but there are sort of various reasons for thinking, actually, let's wait and see what's going on here. So any questions, gamma ray line? It's the particle mass, because there's 2 of them. Okay. Anything else? Right, so let's move on from gamma rays to antiparticles, and in particular positrons. So for a long time, going back for a decade, there's been what's called an excess in the positron fraction between 10 and about 200 GeV. So the positron fraction is number of positrons divided by number of positrons plus number of electrons. Here we've got it as a function of energy. So the first experiments to sort of see this included heat. Then there was Pamela and then more recently, Fermi's actually managed to adapt their analysis so they can see positrons too. So this is the plot that got the theorists excited. We've got, this is the data, and this is the theoretical prediction from expected processes. Now your first thought is, well, this is a lousy fit. But the discrepancy here at low energies isn't necessarily a problem. The number of positrons gets affected by the solar cycle. So it's quite plausible that you could be off down here. But what people were getting excited about was this rise when apparently you'd expect a fall. So you'd argue that there's something producing lots of high energy positrons. And lots of people got very excited about that. However, the big question is, well, I showed you a theoretical expectation, where does that come from? And in fact, it's this line here on this plot. It's what's called secondaries, positrons that are produced when cosmic rays interact with interstellar gas. However, that's not the only non-dark matter source of positrons. And in particular, astrophysical sources like supernova remnants and pulsars can produce positrons. It's something that's a bit hard to calculate, but you can do it. And what you get is this rising thing here, and that's called primaries. And when you add these two together, you get this solid line. Not a brilliant fit to the data, but it is showing that you could find a rise in the positron fraction just from astrophysical sources. You don't need something weird and exotic like dark matter producing extra positrons. But, you know, that's not proven. Could this be due to dark matter annihilation? And it turns out to be really difficult. So as I've sort of emphasized several times, there's this link between the cross-section and the density of WIMPs. So we think we know the density, we think we know the annihilation cross-section, we can calculate the positron flux. And what we get is too small by orders of magnitude to explain this. So you need to find some way of increasing the rate at which dark matter is annihilating, producing positrons. You can sort of do this. You can maybe stick a huge clump of dark matter really nearby us. You can maybe have an annihilation cross-section which changes with energy, so it was very small in the early universe, gets bigger today. Maybe you could say your WIMPs were produced non-thermally, and that gets rid of the relationship between density and cross-section. You can do those things. They're a bit fine-tuned, in particular this idea of having a big clump of dark matter nearby. There's no astrophysical motivation for that. However, the problem is that actually the number of antiprotons you see is completely consistent with what you expect from astrophysical sources. So you've then got to tweak your dark matter model so it produces loads of positrons but no excess antiprotons. And theorists can do that, but the models you end up with end up being pretty unappealing. Similarly, your dark matter annihilation can't produce too many gamma rays or screw up the CMB. So once you put all of this together, my money is on the fact that this positron excess is not due to dark matter annihilation. I could be wrong, but if I had to bet, that's what I'd bet. So, any questions on antimatter? No? Well, future prospects, that's obviously always the question. I've already had the question about this. So in terms of gamma rays, CTA is the next thing on the horizon, an array of Cherenkov telescopes. Antimatter, we've actually, AMS-2 is already launched on the space station. The one general thing I'd say about indirect detection, as in looking astrophysically for dark matter, is that we've demonstrated over the last decade that you give particle theorists some data and we'll produce a model to fit it. So that begs the question, is it possible to detect WIMPs indirectly convincingly, given that we can cook up something to fit anything? And the answer is possibly. And the ways you could possibly do it would be looking for the features in the gamma ray spectrum. And so that is why this line that's potentially been seen in the Fermi data is interesting, because that's something that would be very hard for astrophysics to do. There's also a process called internal Bremsstrahlung that can produce a feature in the gamma ray spectrum at high energies. Again, that's something that's hard for astrophysics to mimic. Another thing you could do would be if you were seeing emission from different sources, for instance, different dwarf galaxies, galaxy clusters, the galactic center with the same energy spectrum, then that could possibly be due to dark matter. It would be hard to explain via astrophysics. And then something that's very difficult to do, but if done carefully could be convincing, what's called multi-wavelength signals. Look for what you'd expect coming out in radio emission given what you were producing at higher energies. So there are things you could do looking for WIMPs indirectly, but it's going to be a case of being very, very careful about it and not just jumping on any excess in any astrophysical data set. So any questions about indirect detection? Right, so that then brings me on to what's called direct detection. And this is looking for dark matter in the lab.
Excuse me, one question.
Yeah.
The detectors in satellites, they don't use Cherenkov radiation, right?
No.
What do they use actually?
And at this point I go, sorry.
No, but they use also, because Fermi, for example, have a calorimeter inside, and the calorimeter is always based on
Okay, they do it.
it's like needle chamber.
Yeah, makes sense.
I mean, it's a complicated process, and in
Yeah.
particular, I think one of the, I mean, I'm going off on a tangent here, but one of the early worries about the Pamela data, for instance, was were they misidentifying antiprotons as positrons? Turns out they weren't, and that's one of the neat things that Fermi checked this. But yeah, there are various difficult, careful processes that they do. Right, so coming on to direct detection. So that's looking for dark matter in the Milky Way halo. So we're sat in the Milky Way galaxy. We think the Milky Way galaxy has a halo of dark matter. And the speed with which the sun is going around the center of the galaxy comes from the depth of the potential well. So basically, from the speed with which the sun's going around the center of the galaxy, we can estimate the local dark matter density. And if we know the local dark matter density, we can estimate the flux of dark matter through this room. And assuming dark matter exists, it's absolutely huge. If you stick your hand out, there will be millions of dark matter particles passing through it every second. Now, because they're weakly interacting, most of them, like neutrinos, will just pass straight through. But a tiny fraction of them will interact with the nuclei of the atoms. And so basically, the direct detection experiments are dedicated experiments built to look for the nuclei recoiling when they interact with the WIMP. So the idea is the WIMP comes in, elastic scatters off of a nucleus, WIMP goes away again, you can't see that, but what you can see is the nucleus recoiling, or at least can detect is the nucleus recoiling. So it's a bit like playing a game of pool, a microscopic game of pool with an invisible cue ball, and you're just trying to look for the coloured balls getting kicked. So there are various ways the WIMP and the nucleus can interact with each other. It can be either spin independent or spin dependent. It turns out that the majority of experiments are most sensitive to the spin independent interactions, so everything I'll show you will be about that, but the general principles also apply to spin dependent, and there are some experiments looking for that. So the thing that's of interest here is the differential event rate, the number of events per kilogram of detector mass per day you run your experiment per kilo electron volt energy bin. And this is the sort of essentials of that expression. So we've got the interaction cross-section on a proton, the local WIMP density, in other words, how many WIMPs there are coming through, the mass number of the target nuclei squared. And the reason that's in there squared is it turns out that it's a coherent interaction with the whole of the nucleus. This thing F is the nuclear form factor, and that just takes into account that, in fact, that the nuclei aren't point particles, they're extended things. So essentially, some of the energy gets absorbed. And then here, from the kinematics of the interaction, we've got an integral over the local WIMP speed distribution, and that's starting from a lower speed V min, which is the minimum speed that can cause a recoil energy of energy E. That's just from kinematics, and that depends on the mass of the target nuclei and the unknown WIMP mass. And one thing to emphasize here, because you've got this mass number squared in here, this is kind of telling you that heavy target nuclei are typically going to be good. And then if you want your energy spectrum out, you're going to have to multiply by the detector mass and how long it's been running for. And that product is called the exposure. And obviously, the bigger your exposure is, the better. So what sort of signals could you be looking for? So as we've already seen from that equation, the event rate depends on the mass of the target nuclei. So here we've got differential event rate, number of events per unit energy, as a function of energy, here in keV from 0 to 100. And I've plotted germanium in red, xenon in dark blue, for 3 WIMP masses, going down 50, 100, 200. So the fall off is most rapid, the lighter the WIMPs are. And so the idea here would be that if you were seeing signals in 2 different detectors made of different materials, you could check that the spectra were consistent, and then you could also measure the WIMP mass. But of course, if you're going to measure a spectrum, you're going to need lots of events. It's not something you could do with a handful of events. There are also some potential events that come from the fact of signals which come from the fact we're sat on the Earth. So the Earth is going around the Sun at about 30 kilometers a second, and the Sun is going around the centre of the galaxy at about 220 kilometers a second. And right now we're going towards a constellation called Cygnus. And so what that means is that most of the WIMPs are coming at us from that front direction. And what that means is that most of the nuclear recoils go into the backwards direction. And so here I've got a plot of the WIMP flux as a function of direction. That's the direction of solar motion. And you can see that almost all of the WIMPs are hitting us from the front. So this is a really large signal. Theoretically, it's really nice. If you had a perfect theorist detector, you'd only need 10 events to show that they weren't isotropic, and you'd only need about 30 to measure this peak direction. However, the huge, I'll get to you in a moment, experimental problem is that to do this, you need a detector that doesn't just measure the energy of the events, it measures their directions. And that's very, very difficult. You absolutely can't do it in a solid or a liquid. You need a gas. And there are some experiments trying to do this, the MTPC, DRIFT, MIMAC and UH, but they're very much at an R&D phase. They're a long way off having experiments that are sensitive on the scales they need to be. Yeah.
So theoretically, if there would be a current of dark matter particles going into a particular direction, into the center of the galaxy or something like that, wouldn't there be some gravitational frame drag effects? Like you have, because of the rotation of the Earth, for example, you have this frame drag effect.
So this isn't really, so the WIMPs, this is assuming actually that their distribution is completely isotropic. Okay. And this is just coming from the fact we're moving through it. So imagine driving a car through the rain. Yeah. So it's our motion rather than anything intrinsic to the WIMPs that's causing this. Anything else? So that, theoretically very nice, experimentally very difficult. But thankfully, this fact that we're moving, it has another potential signal. So what the fact it means is that our net speed with respect to the galactic rest frame is largest in June when we're coming around here, and smallest in December when we're going back round there. And so what that means is the speed distribution in the rest frame of the detector gets shifted as our speed with respect to the galactic rest frame varies. So I've used a very simple speed distribution, might not be right, but it's illustrative, and plotted it in the detector frame in summer and winter. Solid lines summer, dotted lines winter. So they're shifted to higher speeds in summer, so you get more high-speed WIMPs in summer and less low-speed WIMPs. This plot shows the variation in the WIMP flux over the year due to the Earth's orbit. And as you can see, it's pretty small, this variation. And that's because the Earth's speed is so much smaller than the Sun's speed. So if you tried to measure that on its own, that would be tough. But the fact that this shift is speed dependent means that you get an energy dependent modulation in the spectrum. And so here I've plotted the amplitude of the modulation in the spectrum as a function of V min, or equivalently the recoil energy E. And this is much bigger. It can be up to tens of percent. So you get a deficit at low energies that are probably too low to measure, and then a peak at moderate energies that falls off. So this is still fairly small, of order of tens of percent. So you'd need a very big detector, and it would need to run stably for a long period of time. And then, as you can also imagine, the exact shape of this curve depends on the shape of the WIMP speed distribution that you start with here. And that's something that's not very well known. So backgrounds are always the issue with everything. So coming back to experimental stuff, what would you need to do to be convinced that what you were seeing in a direct detection experiment was WIMPs and not backgrounds? Well, there are two different classes of background here. First one, betas and gammas can come in and cause the electrons in atoms to recoil, whereas the WIMPs are causing the nuclei to recoil. There's a second type of background is due to neutrons, produced, for instance, by cosmic rays that come through the Earth's atmosphere or by local radioactivity. And those neutrons are tricksy. They can produce nuclear recoils just like the WIMPs. So there are various things you can do to try and eliminate these backgrounds. The electron recoils, in principle, are easy. So what we're trying to detect is the energy of the nuclear recoil. And depending on what your detector is made of, it can show up as scintillation, ionization, or a rise in temperature. And it turns out that electron recoils distribute their energy between those three channels in a different way to nuclear recoils. In particular, they're more prone to giving ionization. So if you measure at least two of those channels, that allows you, in principle at least, to work out whether you're seeing electron recoils or nuclear recoils. So this, in practice, it's more tricky, but in principle, you can do this and reject those backgrounds. The more tricky background is the nuclear recoils due to the neutrons. And the problem there is that on an event-by-event basis, they're completely identical to the WIMP-induced ones. You couldn't tell what caused it. So the idea is you've just got to block out those neutrons. So you stick your detector deep underground. Reason for that is the Earth blocks the cosmic rays, whereas the WIMPs can go straight through. And then you shield your detector with lead. That also blocks neutrons. And then just be very careful to build everything out of radio pure components. For instance, even just things like glue in a photomultiplier tube can screw up a WIMP direct detection experiment. So before I come on to wrap up with the current results, anybody got any questions on the principles of direct detection experiments? So I'll start with the null results, and the two most sensitive experiments are CDMS and Xenon 100. CDMS is cryogenic germanium experiment, uses phonons and ionization as their way of discriminating nuclear and electron recoils. Exposure before various data cuts, 612 kilograms, energy threshold 10 keV. That's what the detectors look like. Their most recent data set, they saw 2 events in their signal region. However, they were expecting 0.8 background events, so you shouldn't get excited about that. And in particular, reading between the lines, they've been having a problem with what's called surface events. These are electron recoils that happen close to the surface of the detector, so you can only collect part of the ionization, and hence they end up mimicking nuclear recoils. And my understanding is they've now gone away and have been busy working on new style detectors that will avoid that problem. Xenon 100, they've been pressing on. The latest results came from this summer. They've got a 2-phase liquid gas xenon detector, and the 2 things they're looking for are scintillation and ionization. Their detector weighs about 34 kilograms. They've run it for a long time, so they've got a huge exposure. Energy threshold, a little bit lower. Their latest set of results had 2 events in the signal region. They were expecting 1, so again, no sign of anything statistically significant there. And it turns out that their most significant background, again, is the electron recoil. So whilst in principle you can deal with them, in practice, they're a bit trickier. So again, like with the indirect detection, there's been some overexcitement about excesses. So there are a couple of these. over the last 2 years, there's been 2 experiments that have been claiming excesses in their energy spectrum. We've got Cogent, that's made of germanium, but a very different type of experiment to CDMS, much smaller fiducial mass, but also smaller energy threshold. They only use ionization, so that it's much trickier for them to do background projection. And in fact, what they do, they know that a lot of what they're seeing is background, and they sort of say, well, let's fit to what we see using an exponential plus a constant background, because that's typically the sort of shape backgrounds have. They do that, and there's still some events left over that have the sort of spectrum that you'd expect from a 10 GeV WIMP. It's, of course, a huge leap of faith to then say that it is a 10 GeV WIMP. My guess would be that it's, in fact, the background is more complicated than the simple models. Similar sort of thing from CREST, calcium tungstate. Lots of events in their signal region. 4 sources of background they know about, each of which contribute of order tens of events. When they take them into account, there's still about 20 events left over, which could be consistent with light WIMPs again. But again, it could and probably is just the backgrounds being underestimated. One of the things I mentioned before as a potential signal is the annual modulation in the event rate, which comes from the Earth's orbit. And in fact, this is the thing that first got me into the field of dark matter when DAMA first announced they were seeing this way back in the late 1990s. So they've got a really big sodium iodide detector. They've been running it for way over a decade now. And they're very definitely seeing an annual modulation in their event rate. It's at 8.4 sigma. The phase, as in the peak in summer, is roughly with what you expect with from WIMPs. And so what's going on here is they know that lots of what they're seeing is backgrounds, but you hope you're seeing the WIMPs on the top with their modulation. They are definitely seeing a modulation. Whether it's due to WIMPs is an open question. Cogent, this new thing, which was seeing the excess, they then took some more data, and they were possibly seeing an annual modulation in their excess. So, summary of all that mess. There are various hints. They come in 2 forms: excesses above expected backgrounds and annual modulations. The thing to be noted that the 2 experiments that have very low backgrounds, CDMS and Xenon, are seeing nothing. The main issue of all of this is that whilst each of these excesses might individually be interpreted in terms of light WIMPs, it's impossible to come up with a model that fits all of them. And so this is how results from direct detection experiments are usually presented in terms of WIMP interaction cross-section on a nucleon versus WIMP mass in GeV. And so if you're seeing nothing, you get an exclusion limit like this. This is actually a slightly out-of-date one from Xenon. And so everything above that line is ruled out because it would produce more events than they're seeing. And then we have allowed regions, 2 here from DAMA. And the reason why there's 2 is because their detector's made of sodium and iodine. So this region is if it's sodium, and this region if it's iodine that the scattering's happening on. And then also these green regions in here are CREST. And so you can sort of see that yes, DAMA could be due to light WIMPs, but Xenon's coming along fairly convincingly and ruling that out, i.e. if what DAMA was seeing was due to WIMPs, you'd be expecting to see a huge number of events in Xenon. Now, there are huge amounts of things that go getting into the analysis of these plots. At one point, people were suspicious about whether Xenon's energy threshold was as low as they claimed it was. I think it probably is. They've gone away and refined their analysis. There's assumptions that go in about the astrophysics here. The event rate I showed you back here depends on the local WIMP speed distribution. That really isn't that well known at all. However, people have looked and seen, can they cook up something, however bizarre, that makes all these experiments compatible? The answer is no. This is assuming standard WIMP interactions, spin independent. People have tried modifying that, maybe think they interact differently with protons and neutrons. Again, whatever you do, however silly it is, you can't reconcile all of these data sets. So they certainly can't all be seeing WIMPs. And my guess is probably none of them. So future prospects. So these various experiments are teaming up. To go further, you need to build bigger and bigger detectors and push your detector masses up to the ton scale. So the sort of action here is things like Lux, Zeppelin, Eureka, Darwin, and so on. And to give you sort of some idea of where we stand here in terms of theoretical expectations, so here we've got, again, cross-section versus WIMP mass. Here's where xenon 100 currently is. Here's where xenon 1 ton could push down to. In the unfilled contours, these are the sort of a maximum likelihood analysis of the simplest supersymmetric model as of about a year ago. And so these sort of, the probability was tantalizingly laying just below the xenon 100 limits, maybe saying, oh, we can just push down a bit, we'll get it. However, you then fold in the Higgs limits and various sort of other collider searches, and then you then push things down to these shaded regions down here. So looks like it's within the reach of xenon 1 ton, but every plot like this I've shown for the last decade has had the theory regions lurking just beneath the experiments. So either we really are going to get down there and nail it, or we're just pushing the theory down into ever more improbable regions of parameter space. So given all of that, and I guess I probably should say that I am a bit cynical and skeptical about things, you know, maybe it'll all work out in the end. The question is, how do we convincingly detect WIMPs? And I think the way we've got to go here is we've got to, like with cosmology, we've got to look at get convincing measurements of the WIMP properties from different data sets. And the point being that direct, indirect, and collider experiments are all probing different aspects of the same physics. We've got our two dark matter particles come together. We're not exactly sure how they interact, but they interact in some way. Standard model out the other end. So indirect is probing dark matter plus dark matter going to two standard model. Direct is dark matter plus standard model. Collider, two standard model in, two dark matter out. So it's all different ways of getting at the same physics. So if you did start seeing convincing signals in colliders, direct and indirect detection experiments, you then start measuring the WIMP mass and cross-section, and if the answers you get are consistent, then yes, we could really do it. But we probably shouldn't go getting too overexcited about hints in any one experiment via these channels. So to wrap this up, going right the way back to the beginning, hopefully what I convinced you is there's lots and lots of cosmological and astronomical evidence for dark matter that's cold and non-baryonic. My opinion is that we haven't definitively said that modified gravity isn't a possibility, but it's looking really, really difficult to come up with any alternative to dark matter. In terms of dark matter candidate, WIMPs are generically a good dark matter candidate because they're automatically produced in the early universe in the right amount to be the dark matter today. And then going beyond that, supersymmetry, which is the most popular extension of the standard model, gives us a concrete WIMP candidate in the form of the lightest neutralino. So currently WIMPs look like the best bet, but if I'm being 100% honest, there are other dark matter candidates. And there are loads of experiments underway. They've got the sensitivity that if dark matter is in the form of WIMPs, we should be able to get it in the next 5 to 10 years. Maybe a single experiment will be able to see something that's so convincing we let off the champagne corks there and then, but probably convincingly detecting cold dark matter is not going to be due to one single experiment, it's going to be due to multiple things seeing consistent signals. So that's it. Any more questions? Yeah.
About those other candidates, could you say something on axons? How do they fit into the picture?
Probably the best thing is if I get one of my slides up from... Can you wait till tomorrow morning? Or well, it depends if there's any more questions. If there's any more questions, I'll answer those. But if there isn't, we've got time for that one. Yeah.
So the gamma annual modulation, I mean, I think we've been seeing that for quite some time, and I actually didn't even know it's now 8.4 sigmas, and it looks amazingly convincing that at least there's something.
There is absolutely no doubt that their event rate is being annually modulated.
Is there any idea what it is? I mean, of course, I guess there are many systematics which will change during a year.
Exactly. So this is tricky. They have done and published a very careful analysis where they've gone through each of what they think the possibilities are and looked at them. As a theorist, it's very hard for me to sort of judge how convincing that is. At one point, some people were getting very excited. There's an experiment called Icarus, which was located at Gran Sasso with DAMA, and they were measuring a modulation in their neutron background. But it turned out that that then wouldn't work to explain DAMA. I'm not sure of the status of this next explanation now. I haven't heard it discussed for a couple of years, but there's a potassium line lying just beneath the threshold energy of DAMA. That's the background line. And what you could plausibly imagine is if the energy threshold of their photomultiplier tubes isn't constant, perhaps it could modulate over the year as temperature varies. You could then get that. So I think the bottom line is no, nobody knows what DAMA are seeing, but that you can imagine it being something which isn't dark matter. So the best thing, what you'd really love to do, is take the DAMA experiment and stick it in the southern hemisphere. And the closest thing to that I'm aware of is something called DM-ICE. It's a project where they've got a sodium iodide crystal and they've put it down one of the ice cube holes. Unfortunately, it's quite a small crystal and you're going to need a big exposure to test DAMA, but they are hopefully planning to do that, but over a long time scale. So I think really the only way to get to the bottom of DAMA is to do exactly the same experiment, same target nuclei, annual modulation, see what you see. Anything else? Yeah.
Do you happen to have on the slide some super winter or something?
Actually, no, since I've only got 25 minutes tomorrow. So super WIMPs are the kind of idea that you get your WIMP-like particle that's produced in the right amount, but in fact it isn't absolutely stable. It then decays to produce something which inherits the right density, but happens to be extremely weakly interacting and therefore extremely difficult to detect. So I think they're interesting as an existence proof that you could have something WIMP related that will be difficult to show up in a direct or indirect detection experiment. So my understanding, and possibly since you're asking the question you might know more, is that actually then collider experiments are interesting, as in you might want to try and trap the parent particles, stick them in a bucket and wait for them to decay. But no, I think super WIMPs are one of those things we better hope not, but you know, you never know whether the reality's been kind or not. Yeah.
There is this also called wild or conformal gravity by Mannheim. And do you know anything about it? Because
very little.
Like guessing all these galactic curves extremely well.
So I must admit, I haven't looked into that particular theory. Rotation curves, fitting those is doable. What's difficult is lensing. Now, do you know if he's looked into the lensing in that?
Yes, I asked him.
And I guess specific, I mean, when people say they've looked into the lensing, they often just mean that they produce the factor of 2 difference that general relativity gives from Newtonian physics. Do you know if he specifically looked at the bullet cluster? Because my understanding, and this comes from Costas Skordis in Nottingham, who's one of the world experts on these things, that there are various theories that might in principle be able to do the bullet cluster, but that nobody has actually done the calculation that needs doing. And that's not because they can't be asked to do it, it's because it's a really difficult calculation. So that is why I'm not quite as close-minded about modified gravity as some cosmologists are. Some of them would say, you know, we shouldn't even be talking about it, it's nonsense. But as far as I'm concerned, it's not ruled out. So. But yeah, that particular model I don't know much about. There was another question.
Yeah, I was wondering, is there a compelling reason why nature has to be so kind that it gives us the weak interaction that we actually can detect glimpse or anything?
Short answer, no.
So it could be also something like GIMPs, so only gravitationally, and then...
In principle, yes. The reason why we hope not is this WIMP miracle. This thing that if it's weakly interacting, you get the right density. And getting the right density is a more significant thing than you possibly realise. It's easy to fill the universe full of nothing but your dark matter particles or have a negligible density. So to my mind, sort of this WIMP miracle isn't a miracle, but it's just suggestive and means that it is worth investing lots of energy in looking for these things. However, if the cross-section limits start going down too far, then you've got to start thinking again. So if the ton scale detectors don't see anything, then I think personally I'm going to be starting thinking about other things. We're not at that point yet, but there will be a point, I think. Anything else? Well,
it's like a time frame as to when will we have some more conclusive.
So I have a horrible feeling this is one of those things where we always keep saying 5 years and it moves forward at the same rate as time does. So the ton scale detectors really are coming in the next few years, and that really is, I think, the best thing, because I think the sort of plot I just sort of showed, there really is a very definite big improvement coming there. That's not incremental, so that I think is the next big thing. Any final questions? So it's gone 10, so we probably should call it a day, but if anyone's got anything else they'd like to ask, then feel free to come and chat to me. But otherwise, we're done, I think.